Hi, Physics Tube. Mr. Janowski here. This is part 4 of the chapter 36 slides. So we've learned about right-hand rules for the direction of the magnetic field around a current-carrying wire, and a different right-hand rule for the force on a current-carrying wire or a moving positive charge. We learned that there are left-hand rules if you're dealing with negative charges, electrons. You can either use the left-hand rule or you can stick with the right-hand rules and then flip them. And we also learned that if you have a moving charge that enters a magnetic field not perpendicular to it, but at some angle, it's going to actually move in a helical shape. So that's kind of neat. So let's get going with this. I feel like this part might take a while. This is going to get a little bit tricky. So without further ado, let's just get going with this stuff. So what was the first right-hand rule we learned? You're probably getting tired of answering this question. The first one we learned was the grip rule. So that gives you the direction of the magnetic field around a current-carrying wire. And the second one we learned was the cross-product right-hand rule. So this tells you the direction of the force either on a current-carrying wire or on a moving positive charge. So technically a moving charge is of itself a current, so that's why these things are so related. So what is the formula for the force on a current-carrying wire in a magnetic field? F is equal to ILB sine theta. Ignore the cross product one because we're not going to do the real vector math in here. There'll be some stuff with vectors, but we're not going to do the vector math that way. So yeah, here's our formula for that. And what is the formula for the force on a moving charge in a magnetic field? Well, it looks kind of similar to this one. So yeah, F is equal to Q V B sine theta. Q is your charge, V is the velocity of that charge, B is the magnetic field, and theta is the angle between the direction that the charge is moving, the direction of the velocity, and the magnetic field. So sticking to this is something that the astronomy students will probably recognize. So leaving the sun all the time, you have this thing called the solar wind. It's a bunch of charged particles leaving. So think mostly hydrogen and helium nuclei leaving the sun and just shooting out it pretty much in all directions across the solar system. So these things head towards Earth. So now we have moving positive charge heading towards the Earth, and the Earth has a magnetic field. So the part of the velocity that is parallel to the magnetic field is not going to cause any force. So the charge would just want to keep going in that direction. However, the part of its velocity that is perpendicular to the Earth's magnetic field is going to cause it to move in a circular path, and so you're going to get this kind of helical motion down here. So see if you can guess where I'm going with this. What phenomenon does this actually cause? This causes the auroras. So the northern lights or the southern lights. So the light itself is not actually the particles. What happens is the particles come in, they give their energy to molecules in the atmosphere, that were already there. They raise those molecules, electrons, up a level, and then when the electrons jump back down, they give off that energy in the form of light. So you get the auroras. So yeah, hell of a thing, the auroras. Astronomy, you better have remembered that. So we've talked about the direction of the magnetic field from a current-carrying wire. There's a formula for figuring out the strength of that. So the strength of that is given by this formula here. B is equal to mu sub naught times I divided by 2 pi r. So B is, as always, the magnetic field. Mu sub naught is a constant, and it's written kind of funny. Notice it's 4 pi times 10 to the minus 7th. That seems like a weird way to write a number, 4 pi, but that is how we do it. Times 10 to the minus 7th Tesla meters per amperes. So this constant is called the permeability of free space. I is your current in amperes, and R is the distance from the wire in meters. And so this formula will give you the strength of the magnetic field, and you would just have to keep using the right-hand grip rule to figure out the direction of the magnetic field. So this formula works when you're dealing with distances r that are much less than the length of the wire. So when you see these problems, it's always going to be a long wire. What I'm just saying is we're fairly close to this wire. So this would work if your wire were, a meter or 10 meters long and you were just a few centimeters away from this. If you were a meter away from a meter long wire, this formula wouldn't work. It's a calculus thing, actually. So right here, this is saying L, the length of the wire, is much greater than R. So we're talking about a very long wire, L, this way, and a fairly small distance away from that wire. So that's that formula. So what would be the magnitude and the direction of the magnetic field? 0.200 meters directly beneath a long wire carrying 10 amps of current to the right. So first figure out the direction, because that's just the grip rule. So point your thumb to the right, look at the way your fingers, the thumb of your right hand to the right, look at the way your fingers are curling. So your fingers are curling towards you, they're curling down in front, and when you get beneath the wire, they're curling away from you. So this would be going out of the page. So you plug in your numbers, and by the grip rule, I got that wrong. No, it is going out of the page. Ignore that. That's a typo. If the current's going that way, I'm sorry, it's not going out of the page. It's going into the page. Scratch that. I'm all over the place. Yeah, I'm looking at my right hand. So what I wrote is right. What I said is wrong. The current's going to the right. The magnetic field beneath this wire is going into the page. Right. Not a typo. That is correct. Into the page. I'm mixing this up. I'm all over the place. I'm mixing it up with this idea. So now we still have that first wire, and now we have a second wire. So this second wire is 0.500 meters beneath the first wire, and this one's carrying 40 amps of current also to the right. So we're still trying to figure out the magnetic field at this point. So we already know the contribution of this part. We've got to figure out the contribution of this part. So yeah, right-hand rule for the second wire, I2. So point your thumb to the right, and at that point above this wire, the current is coming out of the page. It's coming towards us. So you plug in the numbers, and you get that. So the contribution of this second wire is 26.7 microteslas out of the page towards us. So how do we deal with this? We've got 10 microteslas going into the page from the top wire and 26.7 coming out of the page from the bottom wire. So how do we do this? Well, we add them like vectors. So into the page, call that direction negative. So that's minus 10 microtesla. And out of the page, call that one positive, 26.7 microtesla. Add them together and you get 16.7 microtesla coming out of the page. So yeah, magnetic field is very much a vector thing. So when you're adding components of magnetic fields, you have to add them like vectors. So another quick question. So I've got two wires, one directly above the other. The top wire has got current flowing to the right, and the bottom wire has current flowing to the left. So the first question, think just about the magnetic field caused by the top wire. So do the right-hand rule and figure out what is the direction of the magnetic field at points A, B, and C. So at point A, it should be coming out of the page. At points B and C, it should be going into the page. Right. So now, the second question, does the magnetic field caused by the second wire increase or decrease the the magnetic field caused by wire 1? So at point A, wire 1's going out of the page. So what is the magnetic field from point B, from the second wire doing at point A? It's going into the page. So that one should be decreasing. At point B, the contribution from the top wire is going into the page. So what's the wire 2 going to do? Well, that one's also going into the page, so that should be increasing it. And at point C, the top wire has got a magnetic field going into the page, and the bottom wire has one going out of the page, so that should be decreasing it. So pause this here if you're confused with that and convince yourself that that makes sense. The first question is, what is the magnetic field from the top wire? And then basically the second question is, does the magnetic field caused by the bottom wire agree with or disagree with the one caused by the top wire? So now it's going to get a little trickier. So we've got 4 parallel wires arranged at the corners of a 5 centimeter square. Each wire is carrying 2.5 amps. Wires 1 and 4 are carrying current into the page. So notice you can draw currents this way too. So I'm looking at the tail feathers. This means the current here is going directly away from me. It's going into the page. Wires 2 and 3 are carrying current out of the page. So we've got to figure out what is the magnetic field caused by each wire at a point at the center of the square. So it's just the formula that we just learned. Well, first we need to figure out R. Sorry, getting ahead of myself. We need to figure out R. So if this is 5 centimeters on a side, half the side is 2.5 centimeters. So do a little Pythagoras, get this distance R here. So the distance from this wire to the middle is 3.356 centimeters. Well, that's the distance from all of the wires to the middle. So we've done that. Now that we have R, we can plug this in and we get our answer for B, the strength of the magnetic field. So how do we figure out the directions? This is going to be a lot of right-hand rules. So look at the first wire, point your thumb away from you, and then look at a point down and to the right of that, and notice that the magnetic field caused by this wire should be going down and to the left. Now look at this one. So this current is coming towards you, so hold your thumb out in front of you so it's pointing towards you, and a point lower and to the left of that, well, that should be going down and to the right. So that's this one. And so forth and so forth. B3 coming towards you, right-hand rule means, current 3 is coming towards you. That means B3 is going this way, up and to the left. And for 4, this is a current going away from you. So right-hand rule, that magnetic field will be going up and to the right. So how do we get the total magnetic field at the center of the square? Well, in this case, it's fairly easy. We don't even have to do the math. We've got 4 equal currents, 2 of which are going in opposite directions. And so we've got 4 magnetic fields that are all the same strength. And look at how they're drawn. These guys are just going to cancel. So in this case, the magnetic field at the center of the square is just going to be 0. Different question. So this is not the same question. This time, same wires, same arrangement, but these wires have got their currents going in other directions. This time wires 1 and 2, so the 2 at the top are carrying current into the page, and 3 and 4 are carrying current out of the page. So yeah, we've already done the Pythagoras. We solved for R. We've already done this formula here. So this gives us the strength of each magnetic field, so we have that. So now think for yourself, when you start doing the right-hand rule for all these guys, what are your magnetic field components going to be? So quickly do that. Figure out which way each one's going. So this time it's going to be harder because these guys are not going to cancel. The magnetic field from 1 and 4, the magnetic fields caused by current 1 and current 4 are both pointing down and to the left, and the magnetic fields caused by 2 and 3 are both pointing up and to the left. So the up and down part, they might cancel, but the left part doesn't cancel with left. So we've got to add these guys somehow. So how do we add things like this? Well, we could write them all in angle notation. So flash back to the second chapter we did back in electrostatics. Hopefully this idea rings a bell, but this isn't actually how you're going to add them. What's the other way of dealing with vectors that we learned? Unit vector notation, I hats and j hats. So yeah, it's going to be tricky. You're going to have to do lots of step 1s, so that's what this is and that's what this is, and then you've got to do step 0s. You've got to take vectors that are at ugly angles, so these are ugly vectors, and find their pretty components. So in this case, see how I did this here? I'm looking just at B1, so I'm just looking at this guy. I know what B1 is. I know what this angle is. So I do a little bit of trig, and I figure out this component here. So that was 10 microtesla. And then I'm going to look at my step 0 and figure out the direction. So it's 10 microtesla, but it's to the left. So I should really make this negative 10 I hat microtesla. And maybe you can convince yourself quickly that if this is 10 microtesla to the left, well, this is a 45, 45, 90 triangle. So this side must be 10 microtesla down. So now I've got this guy. So how do we add these guys up? Yeah, we do unit vector notation. So we write them all like this. Convince yourself quickly that I've done these correctly. So everything is going to the left. 1 and 4 are going down as well, so these guys get negatives. Whereas 2 and 3, they're going to the left and up. So these guys get positives for their j hat components. So remember how we add these up. Adding magnetic fields and unit vector notation is fun and easy. Just write them all one on top of each other, line up all your I hats, line up all your j hats, add them all down. So minus 10 I hat times 4 is going to give us minus 40 I hat. But look at the j hat part. So minus 10 plus 10 plus 10 minus 10. So that part just cancels. So we end up with minus 40 I hat microtesla, or you could just say, well, that's just 40 microtesla to the left. So hopefully this angle notation and unit vector notation is ringing a bell from when we did this before. I think this is a really useful skill to have if you're going to keep going with the physics. So I'm bringing it back. So review. What is the formula for the magnetic field around a current carrying wire? So you've got the grip rule, but what's the formula that we learned today? That is B is equal to mu sub naught I divided by 2 pi r, where mu sub naught is this constant, the permeability of free space. So this one is very much a partner to epsilon sub naught, the permittivity of free space that we learned back when we were doing electric fields and things like that. This is the one that goes with it, the permeability of free space. I, of course, is your current, and R is your distance from the wire in meters. So when can you use this formula? You can use it when you've got a very long wire and you're not going too far away from it. So this is saying L is much greater than R. So is magnetic field a scalar or a vector? Hopefully you know this by now. Yeah, magnetic field is very much a vector. We've got these two different right-hand rules for figuring things out. Now we're going to have to do step zeros and figure out components, and we always care about the angle. So yeah, the direction matters a whole lot in this. So magnetic field, definitely a vector. So hopefully you're getting comfortable doing the right-hand rules, and hopefully you can still remember how to do this stuff. And that's it for this part. So hopefully you guys found that helpful.